keep this in mind. It's like, what's the best way to approximate a number? And of course, we don't really know what it means to be a good approximation yet, but just keep that question in mind. Okay. So for example, I want to ask, how can we approximate the number pi? So I think the easiest example is to start with decimal approximation. Okay. So just to get a sequence of approximations, we could say, okay, we'll have 3 is the most basic, 3.1 next is a more accurate one, 3.14, 3.142, and so on. Okay. And so just because we don't really use decimal notation too much once we get past uni, we'll write these as fractions. So we're just doing these as fractions: 3, 31 over 10, 157 over 50, and so on, right? So one of the things that we notice about these is that the denominators are growing very large, right? The fractions are getting quite complex fairly quickly. And I guess we don't really have much of an intuition for whether this is good compared to the accuracy yet or not, but we'll see. So this is like the naive method. But I want to introduce a different method for approximating numbers. And so what we'll do is we'll start with the basic approximation that pi is about 3, okay? Now obviously this is not the best one, so we'll try and make this a little bit more accurate. And how we'll do that is, well, firstly, we'll write pi is equal to 3.014, right, and so on. We'll try and use a recursive method to estimate the error as well. Now the problem is, if we did this, the error would always just be estimated as 0. So the trick we'll use is we'll flip it twice, right? Like x is equal to 1 over 1 of x, we use that trick. So we get that this is equal to 1 over 1 over this, and we calculate that 1 over 0.1415 and so on is about 1 over, well, it's about 7.0625, yeah. So we can, now that we've got a number bigger than 1, we can use this method recursively. So we go, okay, this is about 7, right? So we estimate that pi is about plus 1 over 7, which is 22 over 7, and this is like the classic nice approximation for pi. So it's kind of nice that we're getting this already. Okay, so we just want to continue this recursively. So we say, okay, the next remainder is 0.0625 and so on. So we do the same thing. 1 over that is 15.99, and so on. And we approximate that as 15. So we're not doing the closest number, we're just doing the floor function, okay? And that's so we can use this method recursively. So our next approximation is 3 plus 1 over 7 plus 1 over 15, okay? And if we wanted to calculate that, it would be about 333 over 106. So this is a pretty random method I've shown you, so let's try and see which one is best, okay? So how we'll do that is we'll just write pi is equal to 3.1415 and so on. And well, with the first method, again, here are our approximations. So 3, 31 over 10, 157 over 50, and by construction, they get 1 digit of accuracy each time. Okay. Now with our other method, what we see is they're getting a lot more than 1 digit each time. So 3 is obviously accurate to just the integer part. 22 over 7 we are accurate to 2 dp's. The next one, 333 over 106, is accurate to 4 dp's. The next one, which will be 55 over 113, will be accurate to, I think, 7 decimal places. So they're getting a lot more accurate than this naive version, which is we're trying to say that these look better, right? They somehow look better. They're much simpler fractions in that the numbers in the fractions are smaller, yet the accuracy of their approximations is much better. So that's what we're trying to get at. And so this leads us to the notion of continued fractions. So if we just continue that process out for pi, we can continue that out all the way, what we get is a continued fraction. So we write pi is equal to 3 plus 1 over 7 plus 1 over 15, and then just calculating the next terms as we do, 1 over 1 and so on, okay? And because this is quite big, clunky notation, we often write this in this bracket notation, 3 for the integer part, semicolon, and then all the numbers that we calculated after. Okay, so 7, 15. And for another definition, we call the numbers generated by continued fractions convergence. So, for example, the convergence of pi would be 3, 22 over 7, just these numbers that we've seen before. Okay, so that's just some definitions. And I chose pi because it's a pretty famous number, but it works for any real number x, right? So You do note that it will terminate for rational numbers. We're not going to get infinite continued fractions, but for any real number, we do get this thing. So for a rational x that go on infinitely, we write x is equal to a0 plus 1 over a1. Same thing as pi really. And once again, we have this general notation for them. And the integers we get, a0, a1, and so on, we call these integers the partial quotients. So just for a more formal algorithm, I guess, we'll define a0 is equal to the floor function of x, and we'll have this remainder r0 is equal to the difference, right? And we can do this recursively. So we'll define, if we have an and rn, we can define an plus 1, the next partial quotient, to be the floor of 1 over r, right? Or 1 over rn, sorry, which should be 1 over rn. So just what we'll do before, flip it, take the floor, so approximate it, and then the next remainder will be 1 over rn minus the partial quotient we just got. So that's just formalizing the process we did before. The next question I want to ask is there an easy way to get the convergence if we have the continued fraction? So we have all the partial quotients, can we get the convergence? And so can we do this quickly? So obviously you could just cut it off somewhere, right? And then do the simplification, so 1 over an plus 1 over an minus 1, just keep simplifying it up. But the problem with this is, firstly, if you do it for, say, the nth convergent, this doesn't give you any information about the next one. So let's just think about it for a little bit. If we calculate, say, a0 plus 1 over a1 plus 1 over a2, and then we want to calculate the next one, the fact that 1 over a2 plus 1 over a3, it changes the rest of the calculations, right? So you don't get any more information. So I want to process that if we, for some reason, calculate the 100th convergent, and then we realize I actually want the 102nd one, that we can do that very quickly. We don't need to do another 100 calculations. So the answer is yes, there is a nice process. So it's a recursive process. And so our base cases are, well, the first one is obviously a0. So we'll just define it in terms of the numerator and the denominator. So p0 is a0, q0 is 1. The second one, we can calculate this pretty easily. a0 plus 1 over a1 is, well, a0, a1 plus 1 over a1, right, it's fractions. So p1 is a0, a1 plus 1, q1 is a1. And then there's this nice recursive formula to generate the rest of them. So for all n greater than or equal to 2, we have Pn is equal to An, so this partial quotient, times the previous numerator plus the one before that. Okay, so Pn is equal to An, Pn n minus 1 plus Pn minus 2. And Qn satisfies the same recurrence, it's just that it has different base cases. But it's the exact same recurrence to Qn. Okay? So we have this nice recursive formula, which means that if we have a certain convergent, it's very easy to generate the next one. So I guess let's try and prove this. It's not too difficult. So we can do the base case, right? Just the first recursive one. If we just calculate this, simplify this fraction, right? We'll get a2 over over a1, a2 plus 1. Then just put these all in the same, in the same fraction. Okay, so just not too hard. Just times this by a0. And then if we group up terms, right? So factor a2 out, we'll see that here this is p1, right? The numerator from before, plus a0. So that's our recurrence that we wanted. a2 p1 plus p0. And on the bottom we get the same, right? a2 times a1, which was q1 if you remember, plus 1, which was q0. So we've got this base case. And so again, we'll do this proof by induction. So we're going to assume that it works at any fraction with n terms, right? So because we start at a0, this means it works up to an minus 1. And we've got to want to prove it for a fraction, continued fraction with n plus 1 terms. So again, what we're assuming is that for any continued fraction, we have pn minus 1 is equal to bn minus 1. Just the recurrence works for up to there, right? So the idea and how we relate a fraction with n plus 1 terms to a fraction with n terms is we have a little trick where we basically group the last two terms together. Okay, so we say, well, usually we consider this two separate terms and we'll do the recurrence separately, but here we're just going to add these together and consider it as one number by itself. And what this means is we've now kind of transformed the n plus 1 terms into n terms, so we can just use the recurrence from n terms, which we assumed. Yeah, we can sub this in instead of an minus 1 into the recurrence from before. Then do a little bit of algebra, just timesing the top and bottom by an, okay, and factoring out. And we see that once we do this, we get an outside of this guy, which remember was pn minus 1, plus Pn minus 2, and same on the bottom. We get an outside of this guy, which if you remember was Qn minus 1 plus Qn minus 2. So we get the recursive formula that we wanted. So it's not too hard, and I think it's a neat idea in the proof. So there's a couple of properties that we get from this formula, which is another reason it's nice to have a formula like that. So firstly, I want to note that the recursive formula, it does always work, even when like the an aren't integers. It's just that there's a lot of properties that we miss out on. It will be useful to note that we are allowed to do this, so like the formula works. Now, another thing is that there's just a simple identity here that Pn plus 1, Qn minus Pn, Qn plus 1 is equal to negative 1 to the n, which is just like an induction. And not too interesting in and of itself, it's just very useful for identity. So I'll use here and there. And one thing that we can use this to prove, for example, is that each of the Pn and Qn's we have are a co-prime. They have no common factors. And what this means is that the fraction that we get for the convergent is always simplified, right? So not only is it the correct formula, but it's also the correct formula in the most simple way. So that's very nice. And for just a simple proof of this, if we assume that there's some common factor, say k, right? So Pn is equal to kp dash n and Qn is equal to kq dash n, then we could write this formula, right? The formula we have from here, we could factor out k from the Qn and Pn. So we factor it out, and then what we see is that we have negative 1 to the n is equal to k times some other integer, right? But if we have, two integers is equal to like, some negative 1 or plus 1, well, k has to be negative 1 or plus 1 itself. So, if we assume it's a positive factor, we'll get k is equal to 1, and there's no other possibility for like a shared factor. So, yeah. So that's a nice little proof, and this thing is in general pretty useful for proofs. So now that we went over, continued fractions, I've kind of I've introduced them with by trying to show you, that they're good for approximations and stuff like that, and we've looked at some of their properties. So what I want to do now is convince you that in of themselves they're kind of cool things. So we'll get a bit inherently interested in these objects. So for example, here is the golden ratio, 1 plus root 5 over 2. It has this nice continued fraction. Another one is E, which has this interesting pattern of like 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, 1, 1, and so on. So it's a nice continued fraction for E. E to the 1 over n also has a similar continued fraction where we get like n minus 1, 1, 1, 3 minus 1, 1, 1, and so on. Trig functions like tan. So tan has a very nice continued fraction, 1, 1, 3, 1, 5, 1, 7, and so on. And I haven't really introduced this concept yet, and we won't look at it, but again, it's just for convincing you that they're cool, is we can actually play around with the numerators a little bit, and we get these really nice expressions for integers, sorry, not integers, for numbers. Often pi has some pretty cool ones. So here's one for pi. Again, you can just look at the pretty pattern. There's another one for pi. We get this interesting pattern in the numerators, and here's like one last one for pi. So hopefully that I've kind of convinced you that they're cool in and of themselves, where we're interested in continued fractions and so on. But yeah, so now what I want to do is I want to go back to like these approximations. So that's how we introduce them. And well, I guess the question is, sure, we looked at a couple terms for pi and it seemed like they were good, but like let's quantify this. We're mathematicians, so let's try and quantify how good these approximations are. So yeah, so essentially one thing I want to note before we do this is that if we try and approximate pi with fractions with a general denominator, say d, the best accuracy that we can guarantee is 1 over 2d. So this is a similar concept where if you try and find the closest integer to a real number, the closest you can get is 1 over 2, right? Because say if you're doing 3.5, you can choose 3 or 4. You can always choose one that's a half away. Same concept, but now we're dividing the number line by 1 over d, so it's 1 over 2d. So basically, if we can get a lot better than 1 over 2d, it's looking pretty good, but we'll see about that, okay? So let's do this. Let's compare the convergence of pi to pi itself. So the distance between pi and 3 is 0.14, of course, which is less than 1, a lot less than 1, which is the denominator. Say pi and 22 over 7, the distance is this guy, which all we care about is that it's less than 1 over 7 squared. Which you'll notice is a lot less than 1 over 2 times 7. Similarly, for the next one, pi, the distance between pi and 333 over 106, is less than 1 over 106 squared, which once again is a lot less than 1 over 2 times 106. And same for the next one. We get this pattern of the distance from pi and its convergent p over q is less than 1 over q squared, which again is a lot better than what I said that we could guarantee. So this is a general pattern, we're not going to prove it. It's not too difficult, but we won't prove it. It's just that for all convergence, we will always have the distance between pi and p over qn is less than 1 over the denominator squared. And also this isn't true for just pi, it's true for any irrational x, but just using pi as an example. So this is a really nice property of continued fractions. We introduced them as a way to approximate real numbers, and it turns out they're really good at them. They're a lot better than what you could guarantee, say by doing decimal approximations, something like that. So obviously, it seems like they're very good, but there's a question, right? Like, can we make it better? I chose 2 a bit out of the air, like 103, 104, something like that. So more mathematically, is there a number mu, which is bigger than 2, such that pi minus pn over qn is less than 1 over qn to the power of mu? And for the case of pi, we don't actually know yet. I guess we have some bounds, right? If mu were to exist, it'd be less than around 7 or so, but we don't actually know. It could be 3, it could just be 2. We really don't know. And I guess it's showing that these things are in general quite hard to calculate. So to formalize this a little bit, we'll define this thing called the rationality measure, which is the biggest number mu, such that we can find infinitely many rational approximations, so p of q, to x, such that the distance of x and the fraction is less than 1 over its denominator to the power of mu. And we call mu the rationality measure. And as we've seen, we haven't even calculated it for pi yet, which is the number that mathematicians would definitely try and calculate, so it's very hard to explicitly find. There are some results we know, so we know that all algebraic rational numbers, in other words, if you are an irrational number that is the root of a polynomial, we know that the rationality measure is 2, but for transcendental numbers like pi, we don't know anything in general. And I guess another question that we might ask is, sure, we've seen that convergence to x satisfy this neat property of that the distance is less than 1 over their denominator squared, but is the converse true? If if the distance is less than 1 over the denominator squared, is it a convergent? And unfortunately, no, it's not strictly true. But we can modify it a little bit, just adding a factor of 2. I guess intuitively it's a bit like why we had 1 over 2d before that we could guarantee. If we do this, then yes, if the distance is less than 1 over 2 q to the q squared, then p over q is indeed a convergent. But I guess the problem with this one is that not all convergents satisfy this. So there are some convergents we leave out in this definition. Now, there is like a middle definition kind of between these two that only convergents satisfy, and so they're in some sense the best approximations to numbers. But we're going to go in a bit of a different path. Just for now, know that convergence. Hopefully, you've got a sense that these are really good, and somehow, if you define it properly, they are the best approximations to rational numbers. But the direction I want to go in this talk is I want to show you that continued fractions aren't just useful for approximating numbers. They're useful for other things as well in number theory. So you may not be interested in approximating numbers in of itself. So let's do some solve some fun equations with them. So if you came to the sums talk last week, well, you'll have seen that we tried to solve the equation 2q cubed minus p cubed is equal to 1. And one of the things that you might have gotten from this talk is that it was quite difficult, right? It took a lot of theory, a lot of trial and error and all that to prove this, and we didn't really get a general, a super easy method in the general case. So Pell's equation is a little bit of a simpler version where we change the 3 to a 2, right? So we just get the quadratic version essentially, and I guess we introduce a factor of -1. So Pell's equation is p squared minus nq squared equals 1, where n is some non-square integer. And what I want to show is that continued fractions are a really nice way to solve this. So to start off, let's ask, what is the continued fraction of the square root of 2? The floor of square root of 2, right, is 1.414, something like that. So the first partial quotient is 1. And the remainder is going to be root 2 minus 1, okay? Now for the next term, we should do this little process of flipping it, and then finding, once again, approximating this. So the remainder flipped is this guy, which you can rationalize the denominator to get root 2 plus 1, okay, which is going to be like 2.414, right? So the floor of this is about 2. So a1 is equal to 2, and the remainder is the same as before. It's root 2 plus 1 minus 2, which is root 2 minus 1. Now, because the remainders are the same, this process is just going to go on infinitely, right? We're just going to keep getting the same remainder. And what this means is that the partial quotient is always going to be the same. So for the square root of 2, we actually get this like pretty simple continued fraction that this is equal to 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 and so on. So I guess is this true in general? Let's look at, say, the square root of 7. So if we do this, the square root of 7 is it's between 4 and 9, so the floor is 2, right? So a0 is 2, the remainder is root 7 minus 2. Yeah, so we'll kind of do the same process of flipping the remainder. So if we rationalize the denominator, we get square root of 7 plus 2 over 3, which chucking your calculator, you'll see it's like 1 point something. Say 1 is equal to 1, and the remainder is equal to this guy minus 1, which is root 7 minus 1 on 3. And then the next two steps are just the same thing, repeating the process. Rationalize the denominator, put in your calculator, see what, it's like 1 point something, okay, and just keep repeating this. So the next partial quotient is 1. If you do it again, you see the next partial quotient is 1. And finally, if you get to the fourth step, you'll see that square root of 7 plus 2 is like 4 point something, right? Which makes sense because square root of 7 is 2 point something plus 2, 4 point something. So a4 is 4, and then, well, r4 is root 7 minus 2, yeah? Root 7 plus 2 minus 4 is root 7 minus 2. And once again, we see that that the fourth remainder is equal to the first remainder. So again, what's going to happen is we'll just repeat this process. Because the remainders are the same, the process is going to repeat and repeat and repeat. And notably, we get that square root of 7, I don't have space to write the full continued fraction, so we'll use this like bracket notation, but the continued fraction is 2, should be semicolon, 1, 1, 4, 1, 1, 4, 1, 1, 4, 1, 1, 4, it just repeats. So this is what this line notation means, it just repeats. Okay? So this is a general fact that, that if you have a non-square integer, then the continued fraction of the square root of, say, d, is going to repeat. So again, we don't have time to prove this, it's a bit clunky to prove. But obviously the first term is going to be the floor of the square root, right? Because it's the lowest integer, the highest integer less than it. And then we'll get a bunch of terms, and then we'll finish at 2 times a0, so 2 times the initial term, and then we'll start repeating again. So this is just a general fact for non-square integers, right? The continued fractions of these integers. A fact about this is because the remainder is going to be periodic, the remainder at this step, so when we get 2 times a0, right? 2 times the floor of the square root of d, this is going to be the same remainder as r0, which was, if you remember, the square root of d minus this guy. And so the remainder, so the actual term will be 2 times this guy, so 2 times this guy, plus square root of d minus the floor of that, which is going to be the square root of d plus the floor of the square root of d. And that means that we can write out this continued fraction in an exact way like so. So just replacing their approximation with the actual value. And so this is like an exact expression for the square root of d. It's a bit, bit weird for now, but this is an exact expression for the square root of d. And a fun fact that we won't need, but I guess it's kind of cool, is that these numbers here are palindromic. So a1 is equal to an minus 1, a2 is equal to an minus 2, and so on. It's like a palindromic sequence. And it turns out this is really helpful in solving Pell's equation. So we'll have a little lemma first, and it's just that essentially if you have if you have an irrational number x, and you have some kind of like linear combination of them, right? So a plus bx is equal to c plus dx for integers a, b, c, and d. Then the idea is you can equate the rational parts and you can equate the irrational parts. So the rational parts a and c are equal, the irrational parts b and d are equal. And the proof of this is quite simple. If they weren't equal, then you could write x as a minus c over d minus b, just solving for x, and this means we get x as a rational number. Not true, contradiction, okay? So this is just going to be a helpful step for later on. So we'll now get to solving Pell's equation. We've got everything we need to solve Pell's equation. So it's simple. I'll use a0 here when I'm down here when it'll get too clunky. So when I write a0, it just means the floor of the square root of d. Anyway, so because of this identity that we had before, this exact expression for square root of d, this continued fraction-like expression, what we can do is, even though this isn't an integer, remember the formula works, this recursive formula works even when they're not integers. So we can replace a(n minus 1) with this exact guy over here to get that the square root of d is equal to this guy times pn minus 1 plus pn minus 2. Okay? And once again, the denominator satisfies the same recurrence. So we get this expression for the square root of d in terms of p minus 1 and the denominator is 2, q minus 1, q minus 2. So what we can do now is we can just times the top and bottom by the denominator. Times both sides by the denominator. And what we're going to get is we can equate the components with the square root of d in them and the components without the square root. So we get this equation qn minus 1 times d plus a0 q minus 1 plus q minus 2 times the square root of d is equal to a0 pn minus 1 plus p minus 2 plus p minus 1 times the square root of d. So from that little lemma I had before, we can equate the rational parts and equate the irrational parts. So we say this bit is equal to the rational bit over here. So q minus d is equal to this guy. Okay? And then we can equate the irrational bits. So we get that this guy is equal to p minus 1, right? And we can divide both sides by square root of d, I guess. So yeah, we equate those two parts. And then what we do is we can use our little formula from before, that little minus 1 formula that I said at the start. So this minus 1 to the n minus 2 is equal to p minus 1, q minus 2, minus p minus 2, q minus 1. Then what we'll do is we'll solve for p minus 2 and q minus 2 in these formulas and sub them into this formula here. Okay, so we get q minus 2 is equal to p minus 1 minus a0 q n minus 1. Sub that in here, okay? So we have this here. Once again, do the same thing for p minus 2, sub that in there. And what we see in this equation is that the a0, p minus 1, q minus 1 cancels out, right? It cancels out in both. So all we're left with is this p minus 1 squared term minus d q minus 1 squared. And, well, this is like Pell's equation, right? P squared minus d q squared. It's Pell's equation. And over here, we have minus 1 to the n minus 2. So sometimes it's 1, sometimes it's negative 1. So if m is even, so if the period is even, I guess, we have a solution to Pell's equation. This guy solves Pell's equation. If it's odd, we get a solution to the negative Pell's equation, but we're making progress. Now, one thing I want to do is let's note that if we, instead of stopping after one period, so if instead of stopping after a1, a2, an minus 1 here, we went on for a little bit, so we just extended the continued fractions like 2 or 3 periods or something, the math would stay the same because the final term would be the same. The only difference is the number of terms would be different. So instead of n minus 1 here, we would get, say, 2n minus 1 or 3n minus 1, something like that. So because of that, we can do like k periods, and all the math is going to work. So the only thing that changes in the formula is that we replace m with km in the previous equation. So we do that, we get p k minus 1 squared minus d q k minus 1 squared is equal to minus 1 to the km minus 2. And what we see now is if m is even or m is odd, no matter the period of our continued fraction, we have infinitely many solutions to Pell's equation. Because if m is odd, we just take k as even, right? 2, 4, 6, 8, and this will always be negative 1 to the even number. So we can formalize this as a little theorem. If d is a non-squared integer with this continued fraction, and the m is even, so it has an even period, then for all k, this guy, the convergents essentially are a solution to Pell's equation. And if m is odd, then just all the even guys are a solution to Pell's equation. Okay, so we've got infinitely many solutions to Pell's equation now. So another thing to note is in the odd case, we also get solutions to negative Pell's equation, right? And what that means is we can say take d equals 2, which if you remember from, where was it? If you remember from here, it had just one period, right? It had an odd period. So we can take d equals 2, and we can solve 2q cubed minus p cubed, 2q squared minus p squared is equal to 1, because that's an odd period. And we get infinitely many solutions by taking all the odd k. And what this means is we have like a much easier solution to this guy than the cubic case from last week. So, sure, it's an easier case, but it's cool that continued fractions solves this fairly similar equation. And a natural question to ask is, sure, we've got infinitely many solutions, but are there others? And we're not going to look at this fully, we're not going to prove it fully, but we'll make some steps towards it. So the main thing that I want to prove is that if PQ is a solution to Pell's equation, right? If PQ is a solution to Pell's equation, then P over Q is a convergent to the square root of D. So this isn't too hard to prove. We just look at the distance from P over Q and distance between root D and the P over Q. Just turn this all into one fraction. And then what we're going to do is we're going to rationalize the numerator. Okay, so times the top 1 by Q root D plus P. So we get this with a minus sign out the front. And what we see is that this is just the Pell's equation, right? So this is equal to 1, so we can slot that in, get rid of the negative sign because absolute values. And also the other thing I've done is I've just factored Q out of this expression, right? So we've got a Q squared here, P over Q there. So the distance between root D and P over Q is equal to this guy. And then all we note is that because D is like some integer bigger than 1, we get that square root of D is bigger than 1. And also P is bigger than Q, which if that's a bit confusing, if you can think if Q was like bigger than or equal to P, this guy would be negative, right? Because P squared minus something bigger than it is negative. So P is bigger than Q, both of these terms are bigger than 1 here, so this is less than 1 over 2 squared. Which, again, remember from before, we have this identity that if a fraction satisfies this, it is a conversion. So what we've proved is that, so we proved this theorem. If PQ is a solution of Pell's equation, then P over Q is a conversion to the square root of D. Now, so this is nice, because what it means is that every single solution to Pell's equation comes from the continued fraction of the square root of D. It doesn't yet imply that the ones that we found were the convergence, right? Because we only took like a certain set of the convergence, P, K, N minus 1, and so on. But there isn't, right? We didn't miss any, but we just don't have time to prove that. But it's nice to see that even if there were, right, they all come from the continued fraction. So continued fractions are very, very like useful for solving this equation specifically, and there are others which is also helpful for. Yeah, that's my talk. Are there any questions that anyone wants to ask? Or